Hello friends, in this video we are going to discuss about a previous year GATE question on electronics device. According to the given question, it is given that consider a silicon sample at T equals to 300 K. It means the silicon sample is placed at room temperature with uniform donor density given by 5 into 10 to the power 16 per centimeter cube. So Nd is the donor density illuminated uniformly. Now the semiconductor is illuminated uniformly such that the optical generation rate, that is G optical, will be 1.5 into 10 to the power 20 per centimeter cube per second throughout the sample. The incident radiation is turned off at T equals to 0 and assume low level injection to be valid and ignore the surface effect, and it is given that the carrier lifetime for the hole is 0.1 microsecond and carrier lifetime for the electron is given by 0.5 microsecond. Find the hole concentration at T equals to 0 and find the hole concentration at T equals to 0.3 microsecond. So the given numerical is a problem of illumination of light on the semiconductor, or we can say that light interaction with the semiconductor. So when a light will incident on a semiconductor, then minority carrier generation will take place. So let us consider a semiconductor of silicon. So this is the silicon semiconductor in which Nd doping has been done, and the value of the Nd is given by the numerical, and light has been incidented. Let us consider the light is incidenting on the silicon surface from this direction. So there will be concentration of minority carriers that will be generated at this side of the silicon bar, and this minority carrier concentration or generated or excess minority carrier generation will now decay throughout the length of the semiconductor in an exponential decay manner, and since it is a Nd, that means N type semiconductor, so this will be the decay of the excess holes that have generated due to the illumination of light, and we know that the decay rate or decay equation with respect to time will be given by Pt, and Pt will be Pn0 e to the power minus t by tau p, where tau p is the carrier lifetime for the holes. Now the generation rate is given by G optical, and G optical is given by 1.5 into 10 to the power 20 per centimeter square per second, and we know that the G optical, that is the generation rate of the optical, is given by the recombination rate of the semiconductors also. So it is nothing but Na divided by tau p. So we can say 1.5 into 10 to the power 20 will be equals to Na. Na value is given by Na by tau p, and if we look at the numerical, Na value is not given here in the equation or the numerical. Now this equation Na by tau p. So Na will be Na and tau p value has been given, and tau p is given by 0.1 microsecond. So we can write 0.1 into 10 to the power minus 6 second. So from this given equation, we can find the value of the acceptor concentration, that is Na. So Na will be 1.5 into 10 to the power 13 per centimeter cube. So this is the value of the acceptor concentration inside the n-type silicon. Now we know that from this equation Pt equals to Pn0 e to the power minus t by tau p. So this is the decay of excess holes that have generated, and the concentration of these holes is changing exponentially with respect to time. So we can say that Pt can be written by the equation. So the whole concentration is now 1.5 into 10 to the power 13, and this is nothing but the Pn0, because in the silicon sample we have only doped this Nd value, that is the donor atoms. We haven't doped any acceptor atoms, but there is a value of 1.5 into 10 to the power 13 per centimeter cube of acceptor atom, and hence we can conclude that these acceptor atoms has been generated due to the incident of light, and that is Pn0. So we can write Pt equals to 1.5 into 10 to the power 13 into e to the power minus t by tau p, and tau p is given by 0.1 microsecond. Now from this equation we can calculate the value of Pt, as because we need to find the value of Pt at t equals to 0.3 microsecond. So it will be 1.5 into 10 to the power 13 into e to the power minus 0.3.1. So ultimately the value will be 7.46 into 10 to the power 11 per centimeter cube. So this will be the value of holes at t equals to 3 microsecond, and the value of holes at t equals to 0 microsecond will be this Na value, that is 1.5 into 10 to the power 13 per centimeter cube. So in this way we can calculate the concentration of excess holes due to the illumination of light at different instant of time. Thank you.